So it's my great pleasure to introduce the candidate today, Andrea Allen. We started working together all the way back in 2016, actually, before the pandemic. So it's really exciting to be in a physical room with some of you today, with some of you online. Because it's been a long experience working with Andrea since 2016, but the master's program really took place only over the last 2 years in the pandemic. So I'm just glad that we can do it in person and celebrate the end of a really, really interesting research project together. I should say there was a big pause in between our experience together in 2016. At the time, she was an undergraduate in mathematics, did a research experience over the summer at the Santa Fe Institute, eventually went to industry, learned how to do good software, which we don't always do in science, and had a good questioning period about trying to see how her work could have great impact on the world and how it could be the most useful. Went back to grad school in the beginning of 2020, right at the beginning of the pandemic. And so there's no better way to go about grad school, either through a direct line from undergrad or through industry. I think in Andrea's case, it just means that the path she chose is a little bit longer before you get to the defense, but it also means that the science you're about to see is incredibly mature. I think it's still, mathematics and software, but it's mathematics and software with great focus on how the tools we build can be important for our community, can be useful for the social good, and have a great impact. And I think that's an incredible combination of skill to be able to do technical science that answers important needs of society. So I think it's a really unique master's defense, and I'm really excited for Andrea to present her work to us today. So that said, the microphone is yours.
Great. Well, yeah, thank you both so much. Let me get my shadow of the owl. I think this works. Okay, and then I'm just gonna hide these controls again. Okay, minimize everybody. Okay, great. Yeah, so thank you all for coming today, and those of you in person, and then as well as the group on Zoom. I really appreciate it. I'm about to get started in talking about my research in network epidemiology, and specifically kind of overall, my focus has been on the ways that the contacts within a population change over time, and then how that affects the models of infectious disease that we work with. Oh, now I have to make this clicker work. Okay. So I just want to start off with a couple of thank yous. So first of all, to my advisor, Andrea Dufresne, who's right here today. As he said, we've been working together on and off for a really long time. So it's just really exciting to finally be able to present some of this work that we started back then, and then as well as new work that I've been working on over the last 2 years with him. And then in the same vein, I've been here for 2 years and have been working with the Laboratory for Structure and Dynamics, and have had just an amazing time with everyone in that group, specifically Mariah, who's here, and Nicholas online, for being my co-authors on a paper that we published earlier this year that will be covered in the second half of this presentation. So there's just so many people who have been a part of this for me, and it's been a really positive experience and a great time. So models of infectious disease. So we use models to study how, why, and how fast disease moves through a population. And so models can help answer questions like, how did this happen? How fast can we look at patterns of the way that a disease spread through a population to understand, and then possibly to make predictions for future emerging diseases, or plan interventions and mitigations to help kind of curb what we predict might happen. And so disease modeling, mathematical disease modeling, has been around for a really long time, drawing from epidemiology and biology and the medical field. And then kind of in about the last 20 to 25 years, the field of network epidemiology has emerged. And that's kind of been this fusion of cross-disciplinary fields from mathematics and epidemiology with physics, statistics, and more. And so what makes network epidemiology unique is that we really want to consider the structure and the patterns within the contacts amongst individuals in the population, and then understand how that can potentially make models better and help us answer more detailed questions about spread. So just to touch on the traditional models for disease spread that still kind of are the framework of the disease models I'll be talking about here. We consider the compartmental model, or the family of compartmental models, where the population in question is divided into 3 or more compartments that pertain to the disease status of individuals. And then the way that we track the progression of the disease through the population is by defining a system of differential equations that govern the rate of spread. So in this case, we are considering 3 compartments that's susceptible, infectious, and recovered, where individuals can be in one of those 3 states at a time. The way that the disease model is set up for a given research question depends on the disease itself. So an SIR disease would be one that confers lifelong immunity, where someone to get the disease. There's also the SIS model, where people are infected and then after some period can be reinfected. And so the way that this model is defined is by this system of differential equations, where the rate of change of the infectious compartment is governed by this average spreading rate, or contact rate theta. And so what you can kind of see straight from the equations there is that the model considers the population to be fully mixed. And so that means that infectious individuals and susceptible individuals are assumed to just interact at random and transmit the disease through that way. But we know that empirically, to click on this slide again, populations aren't just randomly mixed. They exhibit some type of structure. So we can use network models or networks to capture that structure, and particularly when the structure is not random or heterogeneous, and that the patterns of contacts between individuals aren't just randomly mixed or homogeneous. And so in my work, in my research here, I've studied the use of networks in disease models to capture that structural heterogeneity of the population. And specifically, I'm going to look at kind of 2 main themes. The first is how that structural heterogeneity changes over time, and then what that means for disease modeling, as well as understanding the population itself. And then I'll also touch on, in the second half, accounting for the randomness involved in the spread of infectious disease. So kind of the overarching theme here is kind of this drive to be able to make probabilistic forecasts for the spread of disease, using accurate representations of the population, considering that these populations change over time. So, so network models. So we can use networks to capture those patterns of contacts between and within populations. But how do we actually do that mathematically? Well, kind of the most straightforward way that I'll first touch on here is by first defining this adjacency matrix that defines a network exactly. And so if you're unfamiliar, let's say we have n nodes or individuals, then we'll have this n by n matrix, where each entry in the matrix between row I and column J would represent the presence or absence of a contact between those 2 nodes, and then 0 otherwise. So using this adjacency matrix A, we can capture the exact structure of a population. And then what we're going to do is we're going to tweak that deterministic model a little bit by still using a system of differential equations, but this time we'll actually have 1 for each node, and we'll be tracking the probability of each node being infectious at a given instant or time t. And those probabilities for each node will be changing as a function of the disease status of each of their neighbors. So what that ends up looking like is something like this, where this top panel tracks the probability of each node being infectious over time. If we were just considering a completely random network where every node was in contact with every other node in the system, each of these sort of traces of those probabilities would look the same, but it's not. We're considering a network with some type of structure. So some have a much higher probability of being infectious at halfway through the process, whereas others stay low until the very end. And then what we can do is to still sort of obtain a clear time series of the expected number of infectious nodes over time, we can just take sum over each of those nodes in the system. So that's just a little bit to get your mind wrapped around what this system of equations mean and what this model looks like. So what it really is just a way to still obtain the same type of solution, but we can incorporate information about that network or about that population and then obtain a more detailed solution that is different from if we just had this traditional assumption of a fully mixed population. So what I'm going to do first is apply this model to explore temporal heterogeneity, and that is considering populations that change over time. So what that looks like is we'll call this a temporal network. And what a temporal network is we're going to define a sequence of consecutive fixed networks or static snapshots, where each snapshot is valid for a finite amount of time, and sort of a sequence of snapshots in a row makes up this temporal network. And where do temporal networks actually come up in the real world? Well, most people at this point over the last 2 years are now familiar with contact tracing efforts. If you live in a bigger city, there are a lot of systems in place where you can sign up for those phone alerts if you've been in proximity of someone testing positive for COVID, for example. And so most of the time this data is collected through wearables, through Bluetooth and mobile phone data. And it's a little bit arbitrary when it's kind of determined at what increment to sample these contacts within the population. So most of the time it's like these 15-minute intervals, or more fine-grained than that, or maybe more coarse-grained. And so we wanted to look at, can we actually use the network structure of contacts to better understand how to both collect and then aggregate that data based on the contact structure. So here we'll kind of use disease spread as a lens. And it's a little bit of a feedback loop problem, because you can kind of motivate this both from, given a set of data, are we able to kind of aggregate these snapshots in a smart way, but you can also look at it from the lens of understanding how to better collect this data from the population. So it's kind of a two-way street. And what we're going to do is I'll start by breaking down the problem just to the kind of individual level, where we'll just consider 2 snapshots at a time, or a pair of snapshots at a time. And so here what you're looking at kind of first off is this small example of a temporal network where we have, let's say we have 3 days of data. And we're going to ask what happens if we combine the day 1 data with the day 2 data. So we leave all of those edges in place, but we just consider that now instead of 2 snapshots, we have a single snapshot that is active for the duration of time of both of them. And so then let's say, so we aggregate that data together. So now we have that day 1 and day 2 combined snapshot. And then let's say we run an infectious disease process kind of over the top of that network. Well, what ends up happening is we potentially introduce an infection that travels through a chain of contacts and ends up in this day 3, infecting nodes in this day 3 network. But we traveled through contacts that occurred in day 1. So we sort of modeled that a disease can be transmitted by traveling back in time. And this is something that this doesn't really make sense. And so we don't want this type of transmission happening in our disease models, because this might impact the validity of the model over time and the accuracy of the results. So then let's look at the other pair. Let's look at day 2 and day 3. And so in that case, when we aggregate those 2 networks, in this case, it's pretty simple because they happen to be disconnected. Then we run this disease process over the top, and we see that it does not violate chronology, which is what we're calling this kind of traveling back in time dynamics. So what we're going to do is we're kind of going to use this as a schematic to progressively look at sequences of snapshots and determine, we want to see if we can determine whether we should or should not aggregate snapshots together. And so how are we going to do that? So we need some type of score or error measure to kind of judge whether 2 snapshots should be aggregated or not. So we're now kind of going to go through the steps in order to derive this error measure that we'll use. So we're going to consider a pair of snapshots at a time. And what we want to look at is, what does the solution of a hypothetical disease process over the top of those 2 networks look like if we were to respect the temporal boundary of the snapshots, and if we were to aggregate those snapshots into one. And so remember that quenched mean field model that I was just talking about. When we solve that system of differential equations, then we obtain this time series of the average number of infections that we expect in the process. And so you can see up in the top right how the temporal solution differs from the solution where we aggregated the two networks into one. And so we're going to be basically interested in kind of quantifying roughly what that area between the curves is, because that's going to tell us how different is the epidemic process solution from the original temporal solution. And so the first thing we're going to do is we're going to borrow a tool from physics, which is here we're using this diffusion approximation, where we're considering this disease process as a diffusion over a network of contacts. And so with some approximation, we can use what's called the, trying to get my clicker to work. There we go. I don't know how helpful that is. We're going to use the matrix exponential, which just approximates the solution to that time series of infected nodes over time. And so all you kind of need to worry about right here is that exponential term with the beta applied to that adjacency matrix A is essentially just capturing the disease dynamics over that contact network and then solving for that. So there's going to be a little bit of shorthand. This T of A function is just how we decided to define these dynamics over the contact network. So, and then the exponential of that matrix is itself another matrix that then when applied to a set of initial conditions, which is that P0 vector, we obtain a solution at each time point. So, so sort of to motivate getting this rough estimate for the area between those two solutions, we're going to estimate the, or we're kind of going to motivate this by seeing what the expected number of infected nodes at 2 time points are. And the 2 time points that we choose is the time point at which we would switch from one snapshot to the next, and then the final time point after the second snapshot has finished being active. So at that first time point, solving for these two solutions in the temporal and aggregate regime is pretty simple. We just take the, we just solve for the dynamics over the snapshot A for the temporal solution and over the aggregate for the aggregate case. And then for the second time point at the end of the second snapshot, things get a little more complicated. So for the aggregate regime, it's still the same solution, just running that process for longer. And also I didn't quite mention, but here what we're considering as the aggregate network is literally the entry-wise sum of those two matrices and then normalized so that the time scale still works out. And then for the temporal case, we have to do something kind of fun here, where first we need to get the conditions that occur after running the process over some set of initial conditions. Then we obtain the state at that switch point, delta TA. And then we run the dynamics over the second snapshot, considering the state of things after the process was run over the first snapshot. So then it might be, it's tempting to want to combine these two exponentials here at the bottom. But again, these are matrices, these are matrix exponentials, which are defined by these Taylor series expansions of powers of these matrices. So we can't really just easily combine these two terms. And the kind of underlying reason for that is due to the fact that matrices don't necessarily commute, which I'll talk more about in a second. So what we're going to do to actually be able to solve for this, this temporal solution is we're going to do a little trick where first we take the log and then re-exponentiate that product of matrix exponentials. And then we're going to use this expression to simplify or express that product, which is known as the Baker-Campbell-Hausdorff formula. And that formula is defined as, we're approximating it here to first order, but it's defined as this infinite sum of terms that involve what's called the commutator of these two dynamics matrices. And what the commutator is, it's literally a matrix itself that is defined by the difference of the product matrix product BA minus the matrix product AB. And what's really cool here is this essentially captures and sort of an entry-wise account of how much these two matrices don't commute. And what commuting means is a commutative set or field or ring is one where A times B equals B times A all the time, and the order doesn't matter. And our problem really here in that aggregation schematic that I showed earlier is questioning whether the order of contacts in these two snapshots matters. So that's really kind of the question we're interested in. And then this commutator term captures exactly that. So we're going to use this as the approximate solution were we to try and solve for the infected nodes at the end of those two snapshots. So what we're going to do, so instead of going straight for that solution, we're just going to take those dynamics matrices and we're going to take the difference between the aggregate solution and the temporal solution. So again, for the midpoint, that's just the really simple difference between the dynamics matrix for the temporal and the that for the aggregate. And then for the endpoint, that difference, once you do kind of a whole bunch of approximation and simplification, we end up with a term that's proportional to that commutator. So now our sort of dynamics matrix that captures the difference between these two solutions is something that corresponds with how much does the order of these two matrices matter. And then what are we going to do with those two terms? So now we have these giant matrices that I'm calling dynamics matrices, D mid and D end. And to actually turn these into something useful, we really want to map these matrices down to a single number or some scalar value that can then be this score or error measure that we're calling CAB. So in order to do that, we take some type of norm of each matrix, and we tried out a whole bunch of things. We also just tried applying the dynamics matrices to some set of unbiased initial conditions. But what ended up working out the most is this norm called the largest singular value norm, or the LSV norm. And sort of intuitively, what it represents is the maximum ratio, or kind of the peak gain of the response of some matrix to an input vector or a unit vector. And so in this case, it kind of represents what is the, if our A here is actually these dynamics, these matrices that are the difference of the dynamics for these two solutions, it captures, well, given kind of a worst case scenario, given any set of initial conditions as this unit vector, what would kind of the peak response or the largest possible response be of this difference of dynamics matrices. So it kind of captures, it takes these whole big matrices and kind of grinds them down to give us a single value that represents how much does the order of these two matrices matter, or how different are these two solutions. And so kind of using the little brackets here to guide the eye, we're sort of creating this crude approximation of that space between these two solutions. And we end up with this measure that's a single number, CAB, that basically demonstrates the extent to which the chronology or the order of the snapshots A and B matters to the epidemic dynamics. So does anybody have any small questions? If not, I'll just keep plowing forward. All that matters really to this point is we are considering snapshots on a pairwise basis. We have A and B. Now we can apply this score to them, this error measure, CAB, that's going to tell us relative to other pairs, how much does the order of these two snapshots matter. So then how can we actually use that? What can we use that to do? There's a couple of things. And the first one that I'll talk about, the first result, is let's say we're given a sequence of 50 snapshots that are each active for some short period of time. And so that's sort of each of these figures, that's that bottom row of lines there shows the time boundaries of 50 even snapshots. And then what we can do is we can recursively apply this error measure to all the possible pairs, pick the pair that has the lowest error measure, or that lowest score, and then which would tell us, okay, of all of these pairs, this pair has the least impact were we to aggregate them together. So then we go ahead and do that. And we can do this recursively until we end up with networks all the way on the far bottom right that have just 4 or 5 snapshots in the system. So we're still dealing with a temporal network, but we're dealing with a lot less data, and we're dealing with a lot less data to keep track of. Yes.
An important clarifying question in the chat. What are the vertical dashed lines on the different snapshot distributions in the previous slide?
Oh, in the previous slide. Oh, over here.
Yeah.
That was just to highlight the mean degree of the network, and a degree is the number of contacts that a node has. So in these two snapshots, on average, our first snapshot had just under 2, and then the second one had just under 4. Thanks. Yeah.
And then in the slide we were at, when you say all possible pairs, do you just mean temporally adjacent pairs?
Yes, that is also a good clarifying question. Thank you for that. Yeah, so considering each adjacent pair, can we smush those? Can we smush those, and so on? Great. So right. So then what we end up with is this system of we still have snapshots, but instead of having 50, we might have 4 or 5. And then when you kind of run the solution of a whole epidemic diffusion process over the top, these green lines represent the solution over that original temporal network, so that original set of 50 snapshots. And then the orange line represents the solution over the new compressed version. And so what you can see is that, you know, even at the level of 7 or 8 snapshots, we still end up with a solution that looks pretty close to those original dynamics, which means that hopefully we could get away with a simpler system and not have to keep track of so much detail. And then how do we actually judge that that makes a difference? Well, the sort of standard way of aggregating data, which is kind of just known as downsampling, is when if you have those 50 snapshots, you say, I actually just want 5. So I'll just take even increments of 10 snapshots and aggregate those together. And so when we compared our algorithm to doing that, most of the time our algorithm performed a lot better at inducing a solution that respected those original temporal dynamics a lot better. And so it's sort of a smarter way than just even downsampling to obtain a simpler network where we're aggregating over data. And then the other way to use it is sort of the step before actually compressing any data. Let's say we have that data, we can just assign that error measure to, again, all possible pairs of consecutive snapshots. And then that can also let us just pick up on the temporal dynamics and the contact patterns of the individuals in that system. So here, so for 3 different resolutions of kind of pre-downsampling of the original data, so that then we can kind of see if we measure that error measure between each pair of snapshots, then we can see there are these long durations where the network is sort of quiet because there's virtually no error induced by combining adjacent pairs. And then there's times when the dynamics are really noisy or loud, where even inducing just a single pair of snapshots might result in a lot of relative error. So right, so this error measure CAB, there's just a couple of kind of things that are evident from these results that suggest kind of future work on this. One is that the algorithm itself, the compression algorithm, is greedy, which if you're unfamiliar with that term, just means that the algorithm doesn't spend a lot of time exploring what the best possible solution is. It just goes ahead and kind of uses that hammer and nail over and over again. So once we start compressing the sort of first pair of snapshots in the solution, and then we progress from there, there's not really a step where we're looking at, is this the best possible version of that simplified temporal network? Or if we started with an original pair that maybe was less good, could we end up with a better solution overall? So that's kind of a point of future work. And then the other thing is the error measure is still just relative to other pairs using in the same network with the same disease dynamics. And it would be really interesting to sort of end up with a normalized score or some type of percentage error so that we could compare compressed networks to other compressed networks that are drawn from different data and sort of have a type of score there that is sort of independent of the process itself. Right, so oops, so that so I just kind of spent all of that time looking at what I like to call horizontal heterogeneity, or the changes in contact patterns as they change over time. But the thing is, we were still using this model that described the average solution over each of those snapshots. And in disease modeling and in the sort of real live process, there's actually a lot of randomness in the spread of disease. And most people have had firsthand experience with this over the past 2 years. I know I have. Perhaps you have had 4 or 5 close encounters with somebody who tested positive for COVID and you didn't get it, and then the 5th time you got it, and become very upset. And and I've just had countless conversations with people where it's like, oh, I didn't get it. Well, it's random. It can be random. And that's exactly one of the things that we really need to incorporate into disease modeling is not only sort of what is the average worst case scenario of things, but what are all of the possible outcomes. And I need to switch that. And so, yeah, right. So on the right, so the gray dashed lines show a whole bunch of realizations of disease simulations over the same type of contact network that I'm showing with this green deterministic solution, using the same initial conditions and the same average contact rates. But here we're simulating what can happen kind of in a real sense when there's all of these different sort of outcomes that we can achieve. So this next part of the talk is really going to be looking at vertical heterogeneity, or the differences in outcomes of an epidemic process kind of beyond just the average. And so from there, we're kind of going to have to use a whole new suite of tools, but the goal is really to make these probabilistic forecasts for the progression of the disease. And so instead of asking questions like, what is the total number of infected people going to be, or how long is it going to take to progress to this fraction of the population, we're going to ask, what's the chance of this scenario happening? If we can sort of figure out what the worst case scenario is, how likely is that to happen? And then that can help preparedness measures and things like that. So what we're going to do is we're going to map away from this deterministic model that relies on these average rates. And we're going to kind of turn this model over into something that deals with probability or chance. And that's going to capture that randomness of spread, which really kind of at the root is about the randomness between individuals in the system. So what we're going to do is we're going to derive this probability value, T, or the transmissibility, which is the probability that a contact between two individuals where one is infectious and one is susceptible will result in a transmission. So the first thing, we're going to temporarily introduce this other random variable, which is going to be tau, which is just going to represent the length of an infectious period for a single node. And so that comes from some distribution. So we can derive or define that cumulative distribution function of tau by using that typical recovery rate from that's sort of borrowed from that continuous deterministic model. And then once we have that cumulative distribution, which would, when asked, would kind of answer what's the probability of somebody recovering before time tau, we can from there just take the derivative of that and derive the probability mass function, which just tells you what is the probability that this node recovers exactly at time tau, so that they have been infectious for exactly time tau. So then equipped with that, now we want to ask the question of what is the probability that, given that they have been infectious for that length of time, what is the probability that the transmission occurs between the infected node and then a single susceptible one? And so we can derive that kind of in the same way from that average rate, but now we're kind of taking this rate and then turning it over into this probability. And so finally, to get the average transmissibility of the system, we're saying that we're considering a whole bunch of nodes, and they each might have this different tau value, this different length of their infectious period. So we can just integrate over all of those possible values to obtain this probability for our system, the transmissibility T, which will be between 0 and 1, that's kind of defined and then related back to these parameters from the deterministic model. So then we're going to take that, and then the other thing we're going to do to kind of change this model from deterministic and continuous to this discrete model is we're going to look at it as what's called a branching process, which is sort of within the name, it's pretty intuitive. We consider, instead of this time series of infected nodes over time, instead we're going to look at this branching of epidemic generations. So let's say we start with a single random node who we're going to call patient 0, and they belong to generation 0. And then anybody that they infect is going to belong to generation 1, and then so forth from there. So kind of this time, instead of being interested in a time series I of t, which would tell us the the time series of infected nodes over time, those curves we were looking at before. We're instead going to be interested in probability distributions of the sizes of the epidemic as it progresses through the population. And so the way we're going to do that is we're going to use probability generating functions, which are essentially sort of a tool that we can use to treat or analyze these branching processes. And I mentioned this before, thanks to that question, but we need to consider the degree distribution of the network. And so the degree of a node is the number of contacts or edges emitting out of one node. And so the distribution, or essentially histogram of all of the degrees in the system, can be sort of housed in this generating function, which is an infinite polynomial where the powers of x are sort of just these counting variables to tell you essentially the coefficient in the distribution with that value. So in this case, P of 1 would be the percentage of nodes that have degree 1, then P2 would be the percentage of nodes with degree 2, and so on from there. And the reason we want to,
Well, before we move on, there's a quick clarifying question about the cartoon you have here and how you label the generations. If the node northeast of patient 0 becomes infected later, does the generation number of patient 0 change?
If the node,
The one that patient 0 does not infect?
Oh yeah, northeast, yeah.
If it does get infected,
then that still belongs to generation 1. So that kind of and it doesn't change the generation of 0. And even if it happens at a later time than the rest, it will still belong to 1, which I think is like a good point to bring up, because the one other thing here that makes this stochastic framework different from the deterministic one is that there's not a perfectly analogous relationship between this generational branching process and continuous time. And so those infections might occur at different times, but kind of depending how you look at things, which I'll talk a little bit about later, actually, the kind of continuous time corresponds mostly with those generations of infection, but that would also depend how long patient 0 is infectious. So ideally things sort of progress along with time, but you can kind of get those little intricacies like that. So yeah, so the reason we have to put this distribution in this generating function and make it all fancy like that is because then we can use really interesting tools to derive other distributions from here. That eventually our goal is going to be to get that probability distribution of potential outcomes of this disease spread process. So the first thing that we're going to do is we're going to kind of attack the degree distribution with that transmission probability T. And so we're going to just kind of quickly define a new distribution that now, instead of defining the degrees of each node, it's going to define the number of infected individuals coming from that node. So that's kind of nice because from the cartoon here, so the degree of patient 0 is 4, but we're now going to derive this new distribution that would represent, what's the chance that patient 0 infects 3 nodes or infects all 4 nodes, and kind of from there. So we do that by just selecting this subset of potential nodes from the degree distribution to be these infectious nodes, and then derive a generating function from there. So this generating function with the T in the argument represents the distribution of number of infections caused by a randomly chosen node, or this random patient 0. And now the next thing we're going to do is it's kind of simple in practice, but what it represents is a little bit intricate. So we're going to take the derivative and then normalize that distribution. And what we're going to get from there is what's called the secondary case distribution. And so what that's going to represent is the distribution for the number of infections caused by a node that was infected from patient 0 or from a previous generation. And the reason this is a different, this distribution will look a lot different than potentially than the original infection distribution is due to a property in network science that's known as the friendship paradox, which I think is really kind of interesting every time I talk about it. But essentially it states that on average, your friends have more friends than you do. And one time I had a friend get kind of upset about this because I told her that, and she claimed that she was the most popular friend, and I said, great, that's why it's an average. You're above average, congratulations. And sort of, but the reason what that really means in this case, especially pertaining to a disease model, is let's say somebody at random obtains the infection, and then you ask, well, how many contacts do they have to potentially spread the disease to? At random, it's going to be drawn from that original degree distribution. But then once somebody else is infected, we've followed an edge. And let's say that edge leads to a node that has 50 contacts. Well, we're 50 times more likely to lead to that node than to lead to a node that just has degree 1, because there are literally more edges in the system emitting out of high degree individuals than low degree individuals. So this distribution is really important because it's going to kind of be the keystone where we derive these distributions of outcomes or cumulative infections based on these patterns of how disease spreads through a heterogeneous population, where some nodes have a lot more contacts than others. And if you're not kind of in this field and you're having trouble following this, just think of people talking about super spreader events. It's kind of the key takeaway here. Some people are going to be super spreaders, and some people have a lot fewer contacts on average. So then what we're going to do is we're going to follow this framework where we define generating functions for these secondary case distributions at each generation of the infectious period. And then from there, finally, to obtain these distributions of cumulative infections, we're going to define kind of this state space of the state that an epidemic can be in at each generation. And so that state is going to just be defined by 2 variables, or 3 actually: the generation, that the sort of most recent generation of infection, the number of cumulative infections, and then the number of new infections. And so through some really kind of beautiful combinatorics, we can take those generating functions of those secondary infections and then kind of stack them up in order to obtain the distribution for the next generation of infections. So kind of underlying this red box, which I don't have time to go into detail with, is just kind of it essentially just turns into a counting problem. And this whole thing is sort of just counting up all of the possible ways that this infection, that this disease can progress through the population. And then ultimately we have that 2-dimensional state space, but what we're interested in for our research, and this is what I worked on with Mariah and Nicholas, is just sort of the distribution of cumulative infections was what we wanted to look at. So finally, we can marginalize over that new infections variable, and then we get a distribution for each generation of what all of the possible outcomes will look like. And so looking at a couple of different networks that have different properties of those original degree distributions, which kind of governs how different are contacts within this population from how different are individuals in these populations from one another. We found that you get this large probability of the disease completely randomly dying out and kind of nothing happening. But then after that, all of the possibilities for the size of this cumulative number of infections over time is really sort of distributed very flatly. And so what that kind of means is if you look at this chart to make some type of prediction, you might say, okay, at the 10th generation, having 400 cumulative infections is just as likely as 50. And that isn't necessarily super helpful when trying to kind of make a decision based off of this. And so if anything, having a distribution like this is more helpful than having a single average, which is what would happen if we just took the mean of one of these distributions. It wouldn't really tell us anything because the mean of a distribution with such a wide variance isn't really very informative. It doesn't really represent what's going on under there. So this model, so that branching process model, which is stochastic, it's able to capture risk as that risk changes over time and the disease progresses through the population. But it also demonstrates why those outbreak sizes aren't well described by an average, which means that kind of that whole original framework that I was just going over with the temporal networks, which is a deterministic framework, which means that we're sort of leaning on the fact that the average is a good descriptor of the dynamics over time isn't necessarily useful in the long term, because we might end up with these average results that are really, really far from what we expect being sort of the best case scenario, worst case scenario. We just have no idea just using a deterministic tool. But hopefully what that means, before I make anybody upset, is that we don't have to throw all deterministic models in the trash. That's not really the goal of this, but kind of what we're leaning toward is the utility of some kind of hybrid approach, where we could use stochastic models for kind of our analysis and for our forecasting, but use these deterministic tools to sort of simplify data and collect data in order to obtain accurate representations of the population. So I actually ended up doing this for kind of a very, very small example where I made sure that that branching process of generations of infection corresponded loosely enough with the boundaries of a temporal network, compressed using that framework that I talked about in the first half, to sort of create a temporal network and then apply this probabilistic forecasting tool over the top of that. And on the top, we're kind of looking at the projections or the solutions to the generating function analysis. And then on the bottom are continuous time simulations to sort of compare against those results. And they match pretty well, which all that kind of does is suggest that this idea of kind of combining these tools could really make for a really interesting kind of loop where we take in data, we compress it into simpler data structures that don't wash away all of the changes and dynamic changes of the contacts that are important to an epidemic spreading model, but then use stochastic methods to kind of analyze and make short-term probabilistic forecasts. So that's kind of the way to tie these things together and have an outlook on an ideal set of models from there. So that is the end. And that first, the second half of the talk is the paper that I mentioned earlier that we published in February and is available online. And then the temporal network framework is available on the archive, updates coming soon. And then if you're interested in any of the software that I wrote and that to support all these models, that is available as well. So thank you so much. I can take questions.
I think I'll moderate the Q&A as I see both the room and the chat. Feel free to raise your hand if you're in the room, or also online. There was one question earlier in the chat that I wanted to go back to, which was about the first half of your presentation. And first of all, I just want to say thank you for the presentation. I think this slide is a good example of what I mean, like being very careful and thoughtful about how your work can have impact with really well prepared packages. And about the first half of the presentation, there was a question earlier, which was, does your result mean you could just sample for snapshots less frequently, I think in the data, rather than aggregate fewer snapshots?
Yeah, so I think you kind of end up in the, like, what I call the trap of theoretical models, which is in order to figure out the resolution to sample at, you would need some type of original data to analyze about, what should we say, analyze that original data and then say, is this working? Are we taking too much? Are we missing things? Are we taking too little? So yeah, so ideally it would mean that you could get some of those questions answered, and then in the future say, oh, we usually like to sample just once overnight, but then during the day we like to sample every 15 minutes to kind of ensure that we're not missing these dynamic.
I see Maggie, you have a hand up online.
Yep. So this was very nice. I'm just wondering, in the work you presented, you're assuming discrete states, that is SI or R or something like that, and also discrete connections. They're either there or they're not. But what if you extended this to more realistic assumptions of, for example, people have a different degree of infectiousness at different time points in the infection, and there's also different degrees of resistance if you've been vaccinated or exposure to prior things or whatever. So I'm just wondering, if you relaxed those assumptions and allowed more continuous states, could you still use the similar approaches with the compartmental model, or would you have to move to an agent-based model, or how would you envision doing that?
Yeah. So there's a couple answers, and some involve work that I've continued doing, and then others are just other answers from the field. But the compartments themselves, there's a lot of variation in that. You can, I mean, I'm sure you know, but there's the SIR model, and then you can add a compartment for E, which is exposed. You can add, these days there's a vaccinated compartment. So you still end up with these discrete state compartments, but they can all represent different levels of risk for individuals. And then the other part from that is if you just keep it on the SIR model, which is a little bit simpler, the generating function framework, we're actually working on something right now to incorporate what happens when you vaccinate some percentage of the population, or introduce other measures there, and then alter those generating functions to represent exactly what you said, which then ends up changing the forecast and changing the probabilistic results by considering a less simplified version of the assumptions that you just mentioned. So
are you saying that you would just like introduce more compartments, or I mean, what about temporal shifts in infectiousness, within a given individual? And each individual might have a different amount of resistance to infection, and the contacts might, you're not just in contact or dot. Some people you have a lot of frequent contact with. So, I'm thinking maybe a weighted graph or something like that. And so I'm just wondering, is there a point where you need to move to a completely different type of model?
Yeah, I mean, I think that usually, so if you have to complicate a model so much that it's just impossible to analyze, then you can move to a different type. But if you can do things like add weights to the temporal networks that either represent the length of that interaction or the contagiousness of that individual, then you can certainly do that. The weighted thing would go right in easily to what I just talked about. Those networks are allowed to be weighted. That's totally fine. But then adding to the branching process framework, you could add a different compartment that would complicate things a little bit, but or you can sort of apply assumptions in other ways by introducing, a variable of that contact rate beta, which could vary between individuals. So
Just one quick follow-up before I stop hogging the floor here. But if you say a weighted network, like where the edges are weighted, could work very easily with this. What about with the time merging stuff that you were doing? Supposing those weights are changing over time, how would that impact the way you would actually merge a number of time steps?
Yeah, so there already is some weighting involved in that, because when we aggregate two snapshots together, you essentially just take the sum entry-wise. So then an edge that appeared in both 5-minute snapshots would then, be weighted so that we can tell that it's active for that whole 10 minutes. Whereas an edge that just occurred in one or the other, just has half that edge density. So it literally, there already is some kind of weighting that goes on in that aggregation of the snapshots. And so if you started with a weighted network that represented severity of the contact, then it would just flow right in, and things would still average out, but you'd be capturing what you said about different pairs having sort of different severity of their contacts.
Thank you.
Thanks.
We have a few minutes left for questions. There's another question online that touches on something I was wondering about, so I'll take some liberty with my moderation and combine two questions. From a practical point of view, say for a Department of Public Health, could that department dial into the model different temporal networks for different populations, for example, within an elderly population or at an elementary school? And I would add to that, I think I'm just curious how your models can help us understand like actual epidemic data, not just contact data, but epidemic data as they come in for a public health department.
Yeah, I think to me that sort of the last schematic of like a feedback loop or like a short-term projection is kind of like what I see. I think we've all kind of learned that the utility of long-term predictions and projections isn't really that helpful when we're constantly getting new data. So To answer the first question, definitely the kind of whole point is to be able to configure that model based on different, precise contact data taken from different populations of interest. So it's kind of meant to be configurable to that. And if not precise data is known, there's kind of a lot of ways within network science and network modeling itself to estimate a network based on things that we do know about that population or based on contact data, and then just feed that in for that specific population. And then back to kind of your question, Laurent, is I think ideally you could sort of start with some baseline of data and then use these tools to make these short-term projections, and then take in new data from there, kind of apply that, make the model better from there, and then make projections from there. But in no way kind of these long-term projections, I don't really see those being helpful in the long term, especially when we have access these days to so much new data all the time coming in about the state of things.
Okay, thank you. We're a minute from the hour. So I'll suggest that we end the public portion of the Q&A, which means that after we thank the speaker again, I'm gonna ask everyone that's in the room to please leave. And we're gonna remove everyone that's currently on the Zoom. But before we do that, please join me in thanking Andrea once again for her presentation. Thank you everyone online. I'll invite only the committee to stay with us, and I will stop the recording.